Statics is one of the basic courses in many engineering disciplines such as mechanical engineering, civil engineering, aerospace engineering, and so on. Statics is prerequisite for many courses too. For most students, it is the first course dealing with real engineering problems. So, understanding statics very well is absolutely crucial for whether you have an easier time in other courses or not. And it kind of sets the tone for how you will perceive your other engineering courses. Mastering statics boosts your confidence significantly to tackle on your other courses that have statics as a prerequisite. The thing about statics is that it has a reputation for being difficult. I think that is absolutely not true. Statics is one of the easiest courses in the curriculum of mechanical engineering. In fact, statics is one of the courses that you can probably summarize it for your non-engineer friends or family members in 10 minutes. My goal here is to teach you statics and make you feel confident to jump at any static problem they may throw at you. I think if done well, learning statics is like learning how to ride a bike. Once you learn it, you know it for the rest of your life. With all this being said, let's get into what we need to know before starting our statics journey. We said that statics is prerequisite for many courses. The prerequisites for statics are 1. Vector calculations. I will give you some examples of what kind of vector calculations I mean in a moment, but if you are not familiar with or comfortable enough with vector calculations, I will leave in the description some links to videos that cover the basics of vector calculations. If you are familiar with vector calculations, then this is going to be a quick review for you. So now, let's get into the examples. Let's say we have vector A that is equal to 4i plus 2j. Again, if you are not familiar with writing vectors in terms of their component, don't panic. Just go to the videos in the description. Okay. Let's say we have another vector b, which is I plus 3j. We should know how to add up vectors a and b. Basically, we add up I components together and j components together. So we will have 4i plus 2j plus I plus 3j, which adds up to 5i plus 5j. Geometrically, if we draw a line from the tip of vector a parallel to b and draw a line from the tip of vector b parallel to A, we will have a parallelogram. The diagonal of this parallelogram that points from the tail of A and B to the point where the two lines intersect is the sum of A and B. That was A plus B. How about A minus B? Well, again, we subtract the I component from each other and subtract the j component from each other. So 4i plus 2j minus I plus 3j, which is equal to 3i minus j. Geometrically, the vector that connects the tip of the second vector in the subtract, which in this case is b, to the head of the first vector, which is vector a here, we will obtain a minus b. The third vector calculation that we should know is the product of two vectors. So here to calculate a dot product b, or a dot b for short, we expand the multiplication term by term. So we will have 4i dot I plus 4 times 3i dot j plus 2j dot I plus 2 times 3 times j dot j. I dot I would be 1, I dot j would be 0, j dot I would be 0 too, and finally j dot j would be 1. Therefore, the dot product becomes 10. Notice that the dot product of two vectors is always a scalar quantity. Here are some properties of dot product as a reminder. A dot b is equal to b dot a. In other words, the order in the dot product is not important. The dot product of each unit vector by itself is 1, and the dot product of each unit vector with other unit vectors in the Cartesian coordinate system is equal to 0 because those unit vectors are perpendicular to each other. By the way, what is the geometrical meaning of this dot product? Well, This number 10 that we got shows the area of the parallelogram that we can construct from A and B. The dot product of two vectors could be a negative number depending on the angle between the two vectors. Therefore, the absolute value of the dot product shows the area of the parallelogram in general. We can prove that A dot B is equal to magnitude of A times magnitude of B times the cosine of the angle between A and B, which I have shown by theta here. This equation is very useful when we have the components of two vectors and we need the angle between the two vectors. In this case, we can write cosine theta equal to A dot B over magnitude of A times magnitude of B. For example, if we want to calculate the angle between A and B here, we will have cosine theta is equal to 10, which was the result of the dot product, over the magnitude of A, which is the square root of the sum of its component squared, times magnitude of B, which is the square root of 1 squared plus 3 squared. If we simplify this, we will get a square root of 2 over 2 for the cosine of theta, which means the angle between A and B is pi over 4 or 45 degrees. We will use this property in statics from time to time. Let's clear things up and put this 10 here. The last kind of vector calculations that we need to know is the cross product of two vectors. Here A cross B is equal to 4i plus 2j cross I plus 3j. Again, we expand the multiplication term by term. So we will have 4i cross I plus 4 times 3i cross j plus 2j cross I plus 2 times 3j cross j. I cross I would be vector 0, I cross j would be unit vector k, j cross I would be minus k, and finally j cross j would be vector 0. If we add up these terms, we will get 10k, where k is the unit vector along the z-axis, which is normal to the display plane. Notice that the cross product of two vectors is always a vector quantity. Here are some properties of cross product as a reminder. A cross B is equal to minus B cross A. In other words, the order in the cross product is important. The cross product of each unit vector by itself is vector 0, and the cross product of I by j is equal to k, j cross k is equal to I, and k cross I is equal to j. To remember these properties, I always put I, j, and k in a clockwise order, and then look if I have to move in a clockwise fashion or a counterclockwise fashion to do the cross product. If I'm going clockwise, the result would be the third vector with positive sign. If I'm going in the counterclockwise direction, the result would be the third vector with negative sign. So to do I cross j, I need to move from I to j in a clockwise fashion. Therefore, the result would be positive k. Similarly, for j cross j, I need to move in the clockwise direction. Therefore, the result is positive I. And finally, k cross I is equal to positive j. But if I want to calculate j cross I, then I need to move in the counterclockwise direction, and therefore the result would be minus k. Let's clean up a little bit. Here is another property of cross product. The magnitude of the vector that is obtained from the cross product of A and B is equal to magnitude of A times magnitude of B times the sine of the angle between A and B, theta. Also, the vector that is obtained from A cross B is always perpendicular to the plane of A and B. To show this here, we need to show the third dimension, which is perpendicular to the display plane. So, here are vectors A and B, which are in the xy plane. The result of A cross B is a vector along the z-axis, which is perpendicular to the xy plane. And that was all the vector calculations that we need to know to dive into statics. Oops, who is this? This is our friend Chuck the Challenger that will be with us during the course. He's gonna jump in once in a while to ask some questions or help us understand some of the topics better. Oh, he's starting right away. So here's a question. Do we really need to learn these vector calculations? That's a very good question. One wonders that if you could do statics all in a scalar mode instead of dealing with vectors, right? Well, the answer is it is absolutely worth it to learn these vector calculations. Granted, it has a learning curve and it takes a little bit of effort to learn these vector calculations. But imagine if you never made a transition from riding a bike to driving a car just because you didn't want to go through the difficulties of learning how to drive. With vector calculations, you will learn statics better, much better. And you set up yourself for success for other courses that come after statics, such as dynamics. So all of that was the first prerequisite for statics. The second prerequisite is, well, that was pretty much it. But some of you might ask, what about calculus? Well, it seems that some people have done some preparation before coming to the class. Very good. The answer is, well, yeah, we need a little bit of calculus in the second half of statics. But I don't want you to go learn or review calculus before diving into statics. For the first few chapters, we don't need any calculus at all. So you are better off to start a journey with statics, and then when the time comes up, we can go and review our calculus stuff before those chapters that need a little bit of calculus. Speaking of chapters, here's the list of chapters that I will cover here. Chapter 1 is all about equilibrium, and it is the most important chapter in my opinion. In Chapter 2, we study structures. In Chapter 3, we discuss distributed forces. We study friction in Chapter 4, and finally, we will have virtual work for the Chapter 5. Before we go, I want to tell you what is the best way, in my opinion, to use these videos to learn statics. I highly recommend you to take notes along watching these videos. Those notes will become a very valuable asset when it comes to midterm and final exams. Also, after watching the videos once, reviewing the notes would be much quicker than watching the videos again. And you can always go back to those notes whenever you need them in the future. I know from practice that taking notes makes watching a 10 minutes video to take twice as much time or even more. To make this a little bit easier, I'm writing a small book that has all the notes you need for watching these videos. This way, you can lean back and have your coffee or whatever your favorite drink is and learn statics. The book is not ready yet, but you can go to my website, mechanicalengineeringwithsam.com, and leave your email there. I will make sure to notify you when the book is out. My goal is to make the book as short as possible while making it a very valuable resource to learn statics. This is why I have named it Statics in 99 Pages, but this might change. And with this, let's dive into statics.